Hi, and welcome to this third and final talk about clustering. In the first video, we have seen the clustering in general. In the second, we have talked about k-means. Today, we are going to see in more details the self-organizing maps, a powerful tool to both cluster and visualize your data. We'll go through how it works, and we'll see the different kind of analysis that we can perform with this model. Self-organizing maps are also called Kohonen maps, from the name of the Finnish professor, Tuomo Kohonen, that can be considered the father of this model. In few words, some learn to recognize a group of similar input vectors in such a way that neurons physically near each other respond to similar input vectors. Basically, they map all the points in a high-dimensional input space from a high-dimensional input space to a 2 or 3D target space, preserving as much as possible the distance and proximity relationship. Self-organizing maps are widely used in data analysis, especially for clustering, data visualization, model estimation, and probability density estimation. Now, let's see the topology. A sum consists of neurons located on a regular grid, and this grid usually have a rectangular or hexagonal structures. Neurons are connected to adjacent neurons by a neighborhood relation. And for example, in these two figures are shown the neighbors of the units marked with a black dot. And as you can see, the structure also changed the neighbor set. For example, with the hexagonal grid, each neuron has 6 first-level neighbors, while in this case, with the rectangular grid, they have 8 neighbors of first level. And when the neighborhood is reduced to 0, the sum acts like a k-means. Now, let's see the prototypes, because each cell is represented by a prototype that is also called a weight vector, and it is d-dimensional, where d is the dimension of the input space. So basically, each map unit can be thought as having 2 sets of coordinates. In the input space, the prototype vectors. In the output space, the position on the map. Now, let's briefly see how the training is done. It resembles vector quantization algorithms like k-means. And in each training step, one sample X from the input dataset is chosen. Then, the distances between X and all the other units are computed. The neuron closest to the input vector is said to be its best matching unit, or BMU. Then, after finding the best matching unit, the weight vectors are updated so that the best matching unit is moved closer to the input in the vector space, as shown in this figure, where you can see that the BMU and also its topological neighbors are all moved towards the sample vector X. And with this model, the clustering is performed by having several units competing for the current object. Actually, it employs both competitive and cooperative learning. It's competitive because the prototype vector most similar to the input vector is modified, the best matching unit, and cooperative because not only the best matching unit is modified, but also its topological neighbors. The first figure shows an example of how the map can learn the data. On the left, there is the initial configuration with the data vectors in red, and they are completely separated from the map. That is on the upper right corner. And after a few iterations on the right, you can see how the map starts actually covering the input space. So this is the sum update rules. that uses a function h that is called the neighborhood function and defines the kernel around the winner unit. Another important parameter is alpha that corresponds to the learning rate. H is a non-increasing function of time and of the distance of unit I from the winner unit C. And the training is usually performed in two phases. First, we tune the map approximately to the same space as the input data, and then we fine-tune it. Now, in this slide, there is a list of parameters that have to be tweaked when you want to use self-organizing maps. For example, we need to choose the map size and its topology. As a rule of thumb, if n is the number of samples, we can choose a number of units equal to 5 by the square root of n. Prototypes can also be initialized in different ways, for example, randomly or drawing them from the input data, basically like we have also seen with the k-means. And training can be sequential, where samples are presented to the map one at a time, or can be batch. So the data set is presented as a whole. And then we need to fix learning rate, we need to choose the neighborhood function and the radii. Now, let's see what data mining questions we can answer using self-organizing maps. So the most important are how to find clusters, which components are the most discriminating, how do the parameters relate to the cluster, and with some, we also have several ways to visually answer these questions, and we'll see them in a moment. So, first, let's talk briefly about labeling that we have already discussed in the previous videos. If we know the class value for some subset of data, we can use it as a gold standard. And for example, we can assign each cell to the class most represented. Now, an important tool in data analysis using self-organizing maps are the so-called hit histograms that show the distribution of the data set on the map. They are formed by taking a data set, finding the best matching unit of each data sample, and increasing a counter in a map unit each time that unit is the best matching unit of one of the input samples. It's also a very useful and easy way to visualize how our gold standard spread on the map, for example, using colors to encode the classes. In this example, there are 3 classes, and you can see that the red one is actually very well separated by the other 2 that have instead some overlap. This is actually a distribution of the iris dataset created by Fisher, when one class is actually linearly separable from the other 2 that are not. Iris is often used as a benchmark. Now, to show the cluster structure, we can use a unified matrix, or U matrix, that shows distances between the neighboring units. This visualization has much more units than the real map, as you can easily see, because also the distances between map units are shown. Now, with self-organizing maps, we can also visualize the map parameter by parameter. So this visualization is called component planes, and with the component planes, we can show the values of the prototype vector for each parameter, and we can use them for correlation hunting. For example, we have the U matrix and then the 4 component planes. And from this dataset, we can easily see that the 2 in the bottom are highly correlated, and we can also infer some other properties regarding the iris dataset in this case. Now, with this method, we can also answer another important question in data mining: which parameters are the most important in discriminating between classes? Basically, we can derive the relative weight of each variable in each map unit. In this example, we can see that the second parameter in green, the histogram in green, is very prominent in the upper part of the map, and so helps to discriminate between the classes really well. Now, we have seen how to locate a sample on the map, but how accurate is this localization? Of course, all the samples are located somewhere on the map, but luckily we can compute two types of errors that tell us if this mapping is good or not. Besides the best matching unit, we can also compute the second best matching unit and the worst matching unit. We can expect that a stable clustering would have the first and second best unit close to each other and far from the worst matching unit. And this can be quantified using the average quantization error and the topographical error. The average quantization error measures the distance from each data vector and its best matching unit. Like in the figure on the right, the straight line is the quantization error of that data point and of those data points. And you can see that the sample on the top has a very, very high quantization error, and so its localization is not good. Then there is the topographic error the topographic error that measures the percentage of data vectors for which the best matching unit and second best matching unit are not adjacent units. So this error gives an overall idea of the goodness of the whole map. Now, another data mapping technique that you can apply using the self-organizing map uses the trajectories. In few words, if our samples are ordered, for example, forming a time series, their response on the map can be tracked at different times. And so we can visually see how a data point goes from a cluster to another where some parameters change or evolve. Now, finally, in this video we have seen the self-organizing maps and how they can be used to ask some important data mining questions, like how to cluster data, which components are the most important, how to locate new objects. And then we have also described two types of errors that help us understand the quality of the clustering and of the single localization. And we have briefly talked about trajectories and how self-organizing maps can use for a time series and to see how an object evolves. And this concludes the clustering series. Thank you for watching.